Welcome everyone, and thank you for joining today's webinar. My name is Piotr Stepien, and I will perform today nonlinear dynamics in NFX lecture and examples. There are also with me Mr. Renier van Vuren from X Solutions, South Africa. Mr. Renier will introduce to you some theory during the lecture part, and he will also show you some interesting practical application examples. This is what we will perform today. So I will start from simple introduction to nonlinear dynamics, and then we will present to you the workflow and setup for nonlinear dynamic analysis problems. I will perform short example. Then Mr. Renier will provide you lecture part about explicit and implicit dynamics, and after that we will show you some project applications accordingly. So let's start introduction. So I think you remember this graph from the previous webinar. This time, once again, I would like to present to you the overview of dynamic analysis. So this graph answers the question what we need to perform dynamic analysis and what kind of output responses can we obtain. So to perform any kind of dynamic analysis, we have to specify dynamic load. Then also mass and stiffness are required, and these two parameters should be always present in your structure or system. And after this, we have to choose the proper analysis type to perform the calculations and to get response as displacements, accelerations, or velocities. You have to remember that most of physical phenomena around you are nonlinear. So just to remind, we talked about the static nonlinearities last time, actually in the one of the previous webinars. So today we will handle these nonlinear problems in the time domain. So you will become more familiar with nonlinear transient dynamic response analysis. All nonlinearities, all nonlinear effects like material nonlinearity, geometrical nonlinearity, contacts will be included. So the next slide shows you the comparison between the implicit and explicit methods. So if you want to perform, let's say, static analysis, you will use implicit method, but today we will handle dynamic problems. So this method, as implicit, will be more convenient to handle slow dynamic problems. For the high-speed events, for the high-speed dynamic problems, like impact problems, explicit method will be the proper one. But if you want to analyze quasi-static, if you want to perform quasi-static simulations, actually you can use both methods. And in midas NFX there is a sequential nonlinear analysis capability, and you can combine both of them to perform this quasi-static simulation. Okay, now I will show you the example about how to use midas NFX in implicit dynamic problems. So I will switch to the software. So you see the simple model which consists of plate and block. So we will start to add parameters to this model, and we will perform, let's say, free fall example. And so this example will show you the slope dynamic problem. So let's assign the material properties, and let's enter the proper values. So 2.1 to the power of 11 for the elastic modulus, 0.3 for Poisson's ratio, and 7,850. Oh, excuse me, I think I have to hide this panel. So now you see the better screen. Okay, so all these data are included. So okay, so we will use the same material definition for plate and block as well. So the second step is the assignment of the property. So I will create two properties. First one related to the 2D, elements. So I will choose the material, and we have to specify the thickness. So this time it will be 2 millimeters. Okay. And let's create the property for the block. Okay, we've got it. The next step is assignment of the contacts. So I'm expanding this branch, and I will add contacts to this model. So I'm clicking on Manual Contacts tab. From the contact type, I'm choosing the general. Of course, it will be surface-to-surface contact. So as the master, I'm selecting all of 3D faces from this model. And as the slave, I will select all of 2D elements. So I'm clicking OK. So this contact pair, as you see, has been created. Okay. Now I'm going to the static tab, and we will apply the constraints. So I'm going to fix both ends. Okay. So the beam has been fixed. And now I will assign the initial velocity for the loads, and also this model will be subjected to the gravitational loading. So okay, let's start from the static load. So let's go to the gravity. Let's check the direction. Okay, it seems to look fine, so I'm clicking OK. And let's add the initial nodal velocity. So I'm selecting all of nodes from the block, and let's enter the value 0.1 meter per second. Okay. Oh, excuse me. We're going to edit, and we will change the direction. Okay. Okay, let's go to the analysis case, and now I will show you how to set up the parameters for the analysis. So let's enter the title. Let's say transient nonlinear. From the solution type, we have to choose this nonlinear implicit transient. Okay, first of all, I will create two subcases. First subcase will be related to the free fall, and the second will provide us the response after the impact. So now I'm clicking the F2 button from my keyboard, and I will change the name for the first subcase to free fall. And I will assign analysis control parameters. So time duration for this example will be 0.2473, let's say. The number of time steps will be 10, and I have to check the geometry nonlinear button. And you have to remember that in this case we are not considering material nonlinearity, but I will show you in the next example how to add this, or maybe FX when this nonlinearity is included. Okay, so we assign the dynamic properties, and right now I'm clicking on additional tab because we have to convert our gravitational loading into the dynamic load. So time function will be constant, and attribute will be global time. Okay. Now I'm drag and dropping this dynamic load set under the initial velocity. As you remember, we defined this parameter. And I'm going to create the second subcase. Let's change the name to impact. And once again, let's assign the analysis control parameters. So I'm checking once again geometry nonlinear option. Time duration for this impact event will be 0.80 seconds with 300 as the number of the time steps. Once again, we are going to add the gravity to the system. And we have to assign the active boundary conditions and load. So just drag and drop the properties. So it seems that our model is ready to analysis. Let's perform the calculations. So you see on the screen the interactive graph which appears automatically after solution run. So using this, you can follow up the solution and monitor your results. As you see, the first subcase has been completed, and now NFX is calculating the response from the second subcase. So we can wait a few seconds, or maybe I will stop execution, and I will show you the results on the model which has been already calculated. And I will show you the results. So I'm going to the results tab. You have to always remember that we are using the real scale for the deformation. So I'm clicking, let's say, total translation output vector. Now I'm clicking on multi-step button, and I will include all of incremental results to our animation. So let's take a look on the results. So I just want to remind you that in this case, we used the linear material, and there was also no damping in the structure. And as you see, we can perform, let's say, slow dynamic events using implicit method. But if you want to add, let's say, some kind of nonlinearity for your material and damping, it also can be done in midas NFX. And in this moment, I'm showing you the animation when the material nonlinearity and damping has been introduced to the system. So you see some plastic stresses are introduced to the plate. Okay, now I want to ask Mr. Renier to perform the lecture. So I have to switch. I will switch to Mr. Renier.
Thank you to the midas team for the introduction, and a very warm welcome to everybody watching this webinar on explicit and implicit nonlinear dynamics. Just to bring everything in context, on our first slide over there you can see our equation of motion, which is really pivotal to this specific field of study. I would guess that for most of us, static linear analysis is what we do most of the times, and the stress strain curve with the depicted green area is really the world that we live in. But another world exists, and that is the purple area underneath the stress strain curve. Interesting just to think about things. When we buy material or specify it, we actually are stuck with the nonlinear capacity of the material, even though we might only use the linear areas. This makes the solution for any linear application quite expensive, since we pay for a lot and we only use very little. Once we move to applications where we really need a plasticity, energy absorption, components that only work once, our solutions can become actually quite economical because we use a lot more of the material capability for the same price that we paid for initially. This example I've just selected, where we can actually have quite an economical solution, really implies that we must have some tools to evaluate our design, our concepts, our analysis, to the extent that our linear analysis software simply cannot provide the results needed to evaluate these events. So let's articulate this actual need that we have. We want to study events where the mass and the damping is now playing a much larger role than we initially would consider for a static analysis. The properties of our components that we want to evaluate is mass, damping, and the stiffness. And those properties are subjected to accelerations, velocities, and displacements. This whole event plays down in a domain which starts at a time t1 and ends at a time t2. So a time domain exists. So this study is characterized by permanent deformation, large displacement, and complex contact right through the event. So what tool will we use? Yeah, you've guessed correctly. It's the nonlinear, explicit or implicit dynamic analysis. Let's just look at the breakdown of the name. You see that the nonlinear really refers to the types of nonlinearity that we can have in our problem. We have material nonlinearity, geometric nonlinearity, as well as a nonlinear contact. On the dynamic side, just means that inertia and resistive forces starts to play a significant role right through the actual time event. And explicit implicit really refers to the way that we go about to calculate the results when we move through this domain from T1 to T2. Numeric integration is really at the heart of finding a solution for our equation of motion. Because we have a mesh, our problem will be described by a finite amount of equations, but it's still a lot. And therefore we will use the numeric methods to obtain the solution. The nature of the numeric analysis is that we will use incremental results right through the domain, and we will add them together at the end. It's really the big difference between the implicit and explicit methods, because they go about differently when approaching the incremental results. Let's have a closer look at the implicit and explicit method. Implicit time integration focus on solving for displacement by means of inverting the stiffness matrix. It's a huge task which requires a lot of CPU and memory. It takes a long time. And the accelerations and displacements are calculated over the time step that we solve for. On the explicit time integration side, we are really interested in solving for the accelerations, which means that the mass matrix needs to be inverted. Now usually the masses are lumped in the mass matrix. So this becomes a diagonal matrix, and the inversion of a diagonal matrix is really easy, it's quick, and the load on the CPU and memory is very low. From there onwards we will explicitly advance the time increment, and we will calculate for the velocity and then the displacement. We have to talk about stability when we talk about implicit and explicit FEA. The implicit method is unconditionally stable. Because it uses linear approximations, it will look for a solution iteratively by using convergence algorithms. The explicit method is conditionally stable, which means it can only be stable if we use time steps that is actually shorter than a critical time step. Let's look at some pros and cons for the different methods. For the implicit method, it is unconditionally stable. It will always tend to converge towards a solution. Also, we have time steps that can be long. We can start with those, and it will actually decrease the time steps if it has trouble to converge. And when it converges, we can assume that a high level of accuracy exists. Although for highly nonlinear problems, we might not find convergence at all. And as already shown, the solution requires the inversion of the stiffness matrix. Pros and cons for the explicit method is the inversion of a diagonal mass matrix. There's no inversion of a stiffness matrix, and we also do not use any convergence algorithms or checks. On the downside, it is conditionally stable. We have to make sure about those time steps, and those time steps are actually being determined by the speed of sound in that specific material, as well as the smallest element length. And I'm showing there at the bottom a small example when the code is actually calculating this. You can see that for element size of 10 millimeters, speed of sound in this specific material at 5,000 meters per second, a critical time step of 2 to the minus 6 seconds is calculated. If we evaluate this event for 1 second, we are going to require about 500,000 increments. Over the years, a lot of work has been done in matching up the explicit FEA results with physical tests. Here is just a few pointers for you going forward to achieve better results, specifically in crash and impact analysis. You have always to remember that it's about wave propagation, and a smooth and clean geometry is much better than one that describes all the small intricacies. You would want to generate a uniform orthogonal mesh. That's a mesh where the mesh lines follow the part boundaries, and you would want to try and maintain the same element size, type and quality throughout. In your crumple or wrinkle zones, you would want a minimum of 6 to 8 elements on the side of the crumple zone to effectively capture the buckle. Also keep in mind that the critical element size, which is the smallest element in your mesh, should be around the material thickness for the best results. Always try to focus on improving the quality of the mesh and increasing the mesh size over a smooth geometry, as opposed to scaling the mass to increase the time step. It is really important to understand that the mesh that you have generated must be adequate to capture the deformed state of the component. And also remember that damping and wave dispersion will occur in unfavorable meshes, even though that mesh might be acceptable or even preferable for a normal stress analysis. Just a quick word on selecting the implicit or explicit method for a specific analysis. In this graph you can actually see that some advantages will exist for smaller mesh sizes using the implicit method due to the computational effort required to invert the stiffness matrix, and the explicit method being a clear choice for very large models, short time span events, which contains a lot of complex contact, material deformation, and large displacements. Here is a list that I will leave open for debate. From my point of view, real slow events like creep, hydroforming, slow deep drawing events will probably fall more to the liking of the implicit method. And as we move through press events, extrusions, roll forming, stamping, buckling, forging, bunching, snaps, and impact and crash, we will move more to the domain of the explicit analysis. An example for the use of explicit analysis. Here is a cable snap event. The application is to design and test a mechanism to grab a cable once it has been severed. Questions that need to be answered from the explicit analysis is, will a loose fitting clamp on the cable still have enough friction so that it can actually grab the cable? And the next issue will be the clamp structure. Will there be sufficient structural integrity to withstand the accelerations and whiplash effects? The next video clip shows the simplicity of the system as well as the recoil event when the cable severs. This is the results from the explicit analysis, where you can see that the cable picks up the clamp immediately, so there was indeed sufficient friction. And this last clip shows the deformation of the bracket under severe whiplash. This video clip shows the physical tests that were done. The slow motion footage shows the first unit that is closest to the point where the cable is severed. My final example shows the application of implicit FEA, where it was used very successfully in designing a machine that will cold roll a circular pipe into a cross section. We have used the implicit FEA to do the concept analysis, making sure that we don't exceed the elongations in the material. Stresses were acceptable. We tested the concept of invoking 4 buckle points through a roller system. We continue to press on the mating surfaces until full buckle occurs, and the profile then finds the mandrel on the inside. Sufficient pressure was added, and on the final picture just before the cross-section photo, you can see that the surfaces were lifted a little bit, and we could see how much springback will occur. In this animation you can see the results of the implicit FEA. The flat surfaces moving towards the mandrel on the inside is actually the cross-section of the rollers as this profile will run through it. At the end of this animation you will see the roller surfaces moving away from the actual profile, and you will see that the residual stresses creates some form of springback in the component. This final animation in the implicit FEA example shows the rollers as rigid surfaces and a section moving through them, inducing the deformed shape that we require. These forces were extracted and applied to the actual machine to make sure that we have sufficient stiffness in our structure to obtain the rolling tolerances. Here you can see the CAD model for the rolling machine with its single stage rollers. Finally, the actual machine that was built and producing these samples that you can see from the round profile to the crossed profile. That then concludes my contribution. I'm going to give you back to Cyprien and Piotr and hope that you enjoy the rest of this webinar.
Okay, thank you, Renia, for the presentation. So now let's take a look on the second example we prepared for you. So I want to show you a quasi-static example using an explicit code with some practical advices. So as you know, we can use explicit code to perform metal forming simulations like rolling, drawing, or sheet metal forming. So, and as you probably expect, at first glance, the implicit solver is the better choice. But however, explicit solvers are more efficient for this class of problems, especially for 3D, where you are facing with contacts and large deformations. So at this moment, I would like to remind that modeling quasi-static events using explicit requires special consideration according to time duration for your event. So it's highly impractical to model the process in its natural time period because we need millions of increments to use in the simulation. So due to this fact, we want to increase the speed of the process in the simulation in the artificial way. So how to do that? Now I'm talking about this because we received many questions from you about explicit code. And actually this is a simple answer according to this topic. So there are two ways. First way is to change the load rates, and the second is to use the mass scaling. So in this example, we will consider only loading rates method. And you have to remember that the goal is always to model the process in the shortest time period in which inertia forces are still insignificant. So this is the one of the many important considerations. So inertial forces are still insignificant. So let's take a look on the example shown on the screen. We see two objects. The big rigid cylinder is impacting a deformable beam. In this model, nonlinear material has been added and both of the ends are fixed. As the dynamic load, I use the time-dependent displacement, and the value for this displacement equals to 0.1 meter. If we go to the analysis, case, we're going to edit, and if we take the look on the subcase control, we see the duration time is equals to 0.005 seconds, which means the impact velocity is 200 meters per second, and this is relatively high. So let's take a look on the results for this model. So this model has been calculated, so I'm just playing the animation for you. So as you see, we obtain highly deformed shape, and as you see, there is no structural response as we expected according to the quasi-static simulation. So we can even say that we are observing some kind of dynamic event rather than quasi-static. So how to actually set up the model to achieve structural response? You have to remember a few things. First of all, we have to assign the proper velocity value to the system. So we have to perform modal analysis to extract the first natural frequency, and this will be the dominant response for your quasi-static. Next step is the calculation, the corresponding time period using the first natural frequency of the model. And after this, we have to estimate global deflection in impact direction. So in our case, it will be 0.1 meter. When we got them, we can calculate impact velocity from simple formula, as you know, distance divided by time. And the general recommendation is to limit the impact velocity to less than 1% of the weight of speed. And this is another consideration or maybe restriction related to the explicit analysis. And typical wave speed in metals, in steels, is very close to 5,000 meters per second. So let me show you the second model. So according to above considerations, this model has been recalculated. First, natural frequency was close to 215 Hertz. And you can easily calculate the corresponding time period is 0.0046 seconds. And from this we can derive the velocity, and it will be 22 meters per second. So it has been estimated properly because this value is around 0.5% of the speed of sound. So let's take a look on the results. So as you see, in this case, the formation looks better, which means we perform some quasi-static simulation using an explicit code. So today I just want to say a few things about a suggested approach. So when we want to perform this kind of simulations, actually we have to perform some series of simulations in the order from the fastest log rate to the slowest. And of course we have to examine the results. So we have to investigate the formed shapes, stresses, strains and energies to get proper understanding for the effects in our model. So that's all for today. We hope we provide you some informative knowledge, and now I'm going to show you a few slides with the project applications, and Mr. Sapien Rusu will inform you about the next webinar events.
Hello. Thank you, Piotr, for the presentation. I'd just like to show you the few slides about a few projects using explicit and implicit analysis. The first one, which is really interesting and have been provided to us by Renier from X Solutions, is the turbine impact analysis. So as you can see in the animation, it's you have a turbine which is rotating at a certain speed. Then a block is impacting the turbine, and you can see that the turbine goes in the opposite direction. So using this kind of explicit analysis, you can predict the plastic deformation of your turbine analysis. So it's very important analysis in for example, aeronautic analysis. So this is the same analysis, but with another angle. And I like to show you another project also, which is a bullet impacting a wall. And this is also this analysis is very short time analysis, so it's also using explicit analysis. And you can see the bullet has been deformed quite a lot. So here you are viewing the von Mises stresses. And this is a displacement. So I wanted to show you also another example about implicit, but we didn't finish the calculation, so you will see the video on our YouTube channel as soon as it is ready. Now, if you want to know more, as I'm telling you about the YouTube channel, here, if you go in this address, youtube.com, use Cyprian R, you will have all the videos on NFX, the interviews of midas NFX users and partners, and a lot of tutorials about every kind of analysis, including explicit or implicit analysis. Now, if you didn't get NFX trial now, you can still request it on our website, midasnfx.com, and we will send you the 30 days trial of Midas NFX. So it includes every module, including explicit, implicit analysis, even CFD, so you can test as you want. And if you need any advice, you have any question, you can ask us also. So I write my email in the format, so it's cyprian@midasit.com. And If you have some question, you can send me some email and I will answer all your questions about NFX. So this is the website, midasnfx.com. Okay, thank you very much to join this presentation. I hope you enjoyed it. And if you have some questions, we can have a few minutes to answer your questions. So just write it in the chat section and we will answer in direct the questions. I saw that some people enjoy the presentation. Well, thank you, really thank you to join this presentation, and we'll organize more webinars about NFX and about everything. So you can always check the webinar planning on the website and join all the courses to know more about FEA and about NFX as well. Okay, I see I have no specific questions, so I just end here the webinar, and I hope to see you for the next session. It will be on the 6th of August, I think, on the car industry. Okay, bye.